We have Maksim Dzabraev, senior engineer from St. Petersburg Research Center. Hello, my name is Maksim. We have Maksim Kalashnikov and Alexander Konitsyn as co-authors. I would like to speak about multi-domain, multimodal transformer for video retrieval. We analyzed video segments on textual queries. We wanted to eliminate bias for specific benchmarks. So we wanted to make a general model which would work with real users. Our model can combine several modalities like static image, sound. As a result, we were able to create state-of-the-art performance on different benchmarks such as LS, MDC, and MSR VTT. You can find our paper at this link. The PDF was at the previous slide. What's the definition here? First and foremost, we have a gallery of video segments called G. On this slide, you can see two video segments. From this gallery, we have textual query named small q. It's a natural language query. There are no limitations for this kind of question, maybe some language-based ones. And it's important to find the most relevant video segments which would correlate to this specific query. Here is an example. On the top right corner, you can see search query, man talking about a car while driving. The system must understand that the image should contain a man. They perform some action, they talk, but they do not just talk, they talk while driving. At the same time, it would be great if a system would understand what do they speak about. Maybe they speak about cars. The standard matrix here is R at K matrix, or recall at K. Here you can see all the details on the slide. It's important to know that the higher the value, the better. At this stage, community has two approaches dominating this problem. First is expert-based, second is conduit training. Expert is pre-trained neural network, which is not trained in our procedure. It has prior experience. An expert takes video or sound as input and generates a set of parameters or a set of slides or frames. Here you can see the key parameters. On the left, you can see that aggregator analyzes these. Well, we have extractors which analyze the video or audio. Then we put them together into aggregator, and then it goes to cosine. Speaking about text, text goes through NLP model. These can be different models, STM or whatever. As output, we get this data, which we can go into cosine, and we can compute similarity. The higher the cosine, the better the relevancy of the query versus the video. We also have 3D convolutional network, which can process 3D videos. We can get frames from the video and have it analyzed by a different independent neural networks. We can also analyze audio by using slow, fast. We can extract speech from sound. We can use OCR to read the text for some ads or for running line. The idea here is that it's very simple to train them, because we don't have to train heavy featured networks. They are separated into different feature blocks. If we have a good feature structure, we will not spoil them by our training. So what I mean by spoiling? The point here is that our community, as of now, does not have enough data to provide full-fledged training for the models. The data is limited, and the probability is very high that the model will be overtrained, which we oftentimes see. Our work is based on MMT work. In the article, we have a dedicated chapter to feature extraction. We've analyzed what to use, what not to use. Here you can see a table on the right. Clip neural network shows very good result, which is better compared to the rest of the neural networks. It doesn't mean that you don't have to combine everything else, but for these results are at 5.5, the results are better. Second approach is clip-based approach. At this stage, we do not have enough data for full-fledged implant training. Either the result be very bad, or the input be very bad, or they will be very fast validated, which will be wrong. We have the single solution for the training. We can have a pre-trained data with a similar task for searching text or video images or query and adapt it to this task. As of now, the community uses clip neural network. They use clip to analyze videos. It's a very deep transformer, and they consider only a few parameters, or they may get rid of the parameters at all. Then they specify the video for specific benchmarks on very low rate, not to spoil the model. It's presented by clip Kamoy, clip to video, and clip for clip. The drawbacks here that you need to fine-tune the model for a specific benchmark, which means that we specialize a neural network. These neural networks cannot be used by a real user. These models are harder to train. We have to spend more resources for training for these video models. We use BERT or Transformer as text model. What kind of datasets we use for this problem? All datasets are similar in structure. They have pairs, video and text. The most popular ones are MSR-VTT and LSMDC. Pay attention that MSR-VTT is very small, only 10,000 segments with 10-hour videos. Obviously, you cannot put all the possible objects, movements, brands, combinations of all these entities together in only 28 hours. LSMDC dataset is considerably larger. On the other hand, it had a different structure. They have 128 full crop movies. These segments are not variable. They are basically single type. I think it's wrong that the community tries to specialize for these two benchmarks. Besides those two datasets, we have quite a lot of different other datasets. You can see them on the right in the table. We've used them in our work. A part of datasets have video as their modality, and another part has image as their modality. It turns out they can be used for videos, but you have to strike the balance between videos and images. You cannot take too many images because they will decrease the performance. We also have VTT datasets, which are significantly larger, but the drawback here is that they gather data from neural network without human participation. They have a lot of noise. You have to be very careful when using them. All these datasets have very similar structure. They have media files and a text which describes this media file. Each text ascribes to some aspect of our life. Our experience demonstrated that it's better to bring together all these data sets in a one big data set and have only one step, one stage for training for all the systems. What do we get as a result? And why should we do this? We had two simple experiments. We took TLMMT and crypto video. Let's take a look at the table on the top left, MMT. Let's put all these parameters and only change the training data set. First, we use MSR-VTT for training. We test all of them and other two data sets. Then the picture will be as follows. If we start on MSR-VTT, and it was pre-trained on MSR-VTT, then the result will be quite good. But if we go to different models, the result will be quite poor. If we use pre-training ActivityNet for pre-training, then we get good results for ActivityNet, but the results for MSR-VTT and LSMD are quite poor. The same applies to LSMDC. But if we have a single unified model, then we will have a model which will work for all three data sets. The results will be better. The same applies for clips to video. If we train a model for LSMDC, the performance will be quite good. But if we retrain it for MSR-VTT and then check it about LSMDC, the score will be pretty low, which means the models are very specialized for specific domains. There are a lot of works, as of now, which use these specialized approaches, which is quite bad. We had a lot of data experiments, and we noticed a law, how training quality and search quality depend on the sample size. On the x-axis we have number of pairs in log scale. On y-axis we have quality of search. The more the better. If we increase exponentially the data set, we have a linear increase in quality for the test. On the one hand, it's very bad because we want to maintain the exponential growth if we want to improve our system more and more. On the other hand, we do not see saturation, and we see some improvement, which is good. The only point here, the only drawback here, is that almost all data sets applicable for data sets were designed with the help of humans. I hope that in the future our community will be able to find a way to mine data from the internet and have indefinite sampling from the network. Besides that, maybe it's possible to go online without the need to actually connect the data. You can just go online, analyze, and then delete the data. And the final table, we have two approaches, CAMOA and MDMMT. They show good results for MSR-VTT, CAMOA and clip to video, but these are very specialized, tailored solutions, and they work significantly worse than other models. Our model shows basically the same score, but they can work better on other domains, and they can work with an end user. In our work, we set and estimated the generalization problem. We found the log linear generalization law. We explored a large number of pre-trained experts. Now we understand which are applicable for this task and which are not. Our solution is based on an MDMMT approach. We've demonstrated that images plus text, or the search query in text, can use not only videos but also images plus video. But you have to combine them in a proper way. We've used a deeper aggregation model. We also had a longer training period as we had more data, and we had a more aggressive dropout. Thank you. Thank you, Maksim. Maksim Dzabraev, senior engineer of St. Petersburg Huawei branch. We spoke about MDMMT for semantic search. It was very interesting to listen to your presentation.